Hi guys. So I don't have my book with me. Long story. Anyway, I'm going to do my best to go over everything that I know comes in the next section of chapter 5, which is complex numbers, imaginary numbers, and radical numbers. Okay, but what we're going to do first is we're going to start with imaginary numbers and how to graph those in an imaginary plane. Okay. So, say we've got these axes here. If we were not talking about complex numbers, these would be the x and y axes. But because we're talking about complex numbers, the x axis is what we call the real axis, and the y-axis is the imaginary. So if we wanted to graph something like 3 plus 2i, okay, that is the standard form of an imaginary number, which is a plus bi, where a is the real part and b is a number that's stuck to the imaginary element, the I. So A is the real part and B is going to be the imaginary part. So if we were to graph 3 plus 2i, we're going to go along the real axis 3 units and then up 2 along the imaginary axis. So that would give us this point right here. Start at the origin, go right 3, and then go up 2 because our 2 is positive. Okay, so another example. Let's graph. We'll do one in, say, every quadrant here, okay? Okay, so now let's graph negative 4 plus 2i. Okay, negative 4 is the real part of that number, and then positive 2 is the imaginary part. So we'll go negative 4 along the real axis, up 2, and that is our point right there. Okay. Another, putting us into a different quadrant, let's do negative 3 minus 1i, or just I. So negative 3 is the real part, and negative 1 is the imaginary part. So we'll go 3 to the left from the origin, down 1, and there's our coordinate. Okay, very simple. And then for the last quadrant, quadrant 4, let's graph 5 minus 4i. Okay, so we're going to go 5 to the right and down 4. 1, 2, 3, 4, 5. 1, 2, 3. Puts us right about there. Okay, so this is the example that we're going to use to find the length of these absolute values, as the length of these imaginary numbers as they are graphed in a coordinate plane. Okay, so there's the coordinate right there that represents 5 minus 4i. So the magnitude, or the modulus, the length of that pink vector there, is found using Pythagorean's theorem. Okay, so we've got a right triangle now, and we've gone over positive 5 and down 4 to get to the coordinate that we plotted that represented 5 minus 4i. So we can find the length of that by putting under our square root 5 squared plus negative 4 squared. Okay, that's the Pythagorean theorem. And then when we take the square root of that, we're going to get the length. So 25 negative 4 times negative 4 is 16. So we get the square root of 41. 25 and 16. Yeah, the square root of 41. So because that does not simplify, we have the modulus, or the magnitude of that vector, that complex vector, is the square root of 41. Okay, so that's how you graph it, and then how you find the length. So let's look at another one. Okay. Okay. So let's graph, I don't know, 4 plus 2i, and then find the modulus, or the length of that vector. So we'll go right 4 up 2. There's our coordinate, and this is the length that we are looking for. Okay? Which again is the hypotenuse of this right triangle. So 4 squared plus 2 squared is equal to c squared. Remember, a squared plus b squared equals c squared. And then we want to take the square root of 4 squared plus 2 squared in order to find the length of c, which is our hypotenuse. So 16, 4 squared is 16, 2 squared is 4. So we get the square root of 20. So we need to simplify that radical, okay? So we're going to simplify the square root of 20. So we're going to start with 20 over there on the left side of that table and divide it by the smallest prime, which is 2. 20 divided by 2 is 10. The smallest prime that divides 10 is 2. 10 divided by 2 is 5. The smallest prime number that divides 5 evenly is 5, and 5 divided by 5 is 1. Okay? So this is the prime factorization of 20. What we need is the simplified radical. So because we're finding the square root, we're going to group what's in the right-hand side of this table, group like numbers in groups of 2. Okay, so I've got 2 2s, and then I've got one little loner guy, that's the 5. So to simplify the radical, I'm going to pull one of those 2s, and that goes outside the radical, and the dangler guy goes underneath the radical. So the length, or the modulus of that vector, is 2 times the square root of 5, okay? And because it doesn't matter what quadrant that vector is in, it's always positive, because when you square a negative number, you're always going to get back a positive. So as you're doing the work or going through the IXL for this, you may find this as the representation of your imaginary or complex number, okay? Because that absolute value symbol represents the length of that vector. And length, which is a distance, will never be negative. Okay, so we may have something that looks like, okay, we may have something that looks like this. We are told to find the length of that particular vector, okay, represented by 8i. Now, if it's only 8i, the imaginary part of that is 0, okay? So the real part of that number is 0 plus 8i is our standard form of that complex number. So when we graph that, we don't go anywhere on the x-axis, we just go up 8 along the imaginary axis. So 1, 2, 3, 4, 5, 6, 7, 8 puts us right there on the imaginary axis. And if we want the length of that vector, which is this right here, okay, we are going to do the square root of the real part squared plus the imaginary part squared. So 0 squared is 0, 8 squared is 64, and of course the square root of 64 is 8. Okay? So that's how you graph when you've got no real part included inside your absolute value symbols, okay? It's implied that it's a 0 if there's no real part there. Okay. So now what we're going to get to is adding, subtracting, multiplying, and dividing complex numbers, okay? That's the standard form of a complex number. A is the real part, B is the imaginary part. So either one of those could be positive or negative. It's not literally A plus BI, where A is always positive and B is always positive. A could be negative and B could be positive, okay? Like -3 plus 2i. Or A might be positive and B is negative. Or maybe they're both negative. Okay? So A plus BI is not a literal, to be taken literally, okay? A can be negative and or B can be negative. And then, of course, that determines what quadrant on the imaginary or complex plane you're in. Okay? So what we're going to do is we're going to add and subtract these imaginary numbers, starting with addition because that's the easiest thing to do with these. So say we are adding, say we're adding 6 plus 3i to -2 minus 4i. And we are adding those. Well, we know that at this point in our mathematical careers that you can only add and subtract like terms, okay? So the best thing to do here is to group your like terms together. Those are the A values. Those are the real parts of those imaginary numbers, and these are the imaginary parts. So I will group them together. 6 plus a -2, that will give us our real part, and then the imaginary part is 3 minus 4, okay? With a plus in between. Okay, so 6 plus a -2 is the same thing as 6 minus 2, which is 4. And then 3 minus 4 gives us a -1i. So when we add those two complex numbers, we get 4 minus I. Okay? Easy enough. So let's do another addition. Okay? Negative 6 minus 3I plus negative 2 minus 6I. Okay, so we've got the real parts of those numbers, and then we've also got the imaginary parts. Okay, so we'll put the real parts together, negative 6 plus a negative 2, to which we are adding the imaginary parts, negative 3 plus a negative 6I. So negative 6 plus negative 2 is negative 8, and negative 3 plus negative 6 is our negative 9I. So our complex number is negative 8 minus 9I. Very, very basic. Okay, so we can do the exact same thing with subtraction. So we're going to keep these same two complex numbers, and instead of adding them together, we are going to subtract them. Okay, so we'll have a minus sign in between. Now, you have to be aware of the fact that when you subtract here, that's the same thing as distributing in a negative 1. Okay, so when we subtract, we could actually rewrite this whole entire thing and change it from a subtraction to an addition. Okay, so negative 6 minus 3I plus, now we're going to distribute that negative 1 into that set of parentheses. So negative 1 times negative 2 is positive. Negative 1 times negative 6I is also positive. Now that we've rewritten it, changed it from a subtraction to an addition, now we can just combine our like terms and add. So negative 6 plus 2 is negative 4. Negative 3I plus 6I is a positive 3I. Okay, let's do one more subtraction. So negative 2 plus 3I minus 4I. Okay, now the missing real part of that 4I is 0. So let's start out by rewriting that in standard form. Okay, now we are going to distribute this negative 1 here, and then we'll rewrite that subtraction problem as an addition. So negative 1 times 0 is still 0, and negative 1 times positive 4I is negative 4I. Now we can group our reals together and our imaginaries together. Negative 2 plus 0 is negative 2, and 3I minus 4I is negative 1I, or just minus I. Okay, so adding and subtracting, very simple. Now the next thing that we're going to do is multiply. And when we multiply, we need to remember from the previous lesson that I squared is equal to negative 1, and the square root of I squared is equal to I. Okay, that's our key that we're going to use to write our final result in standard form. Okay, so let's say we are multiplying 3 plus 2i by negative 2 minus 4i. Okay? We're going to FOIL this just like we would if these were regular, say, x plus 5 times 2x minus 1. Okay? We're going to FOIL that out. So we'll start right here with the multiplying and get negative 6. And then we'll go from 3 to negative 4i. So 3 times negative 4i is negative 12i. Then we will go from the positive 2i times negative 2, which is negative 4i. And then finally, we'll go from the positive 2i to the negative 4i. So positive 2 times negative 4 is negative 8, and I times I is I squared. Okay? So we're going to go back to the beginning, and we are going to combine like terms, which are these I values right there. So negative 6 minus 16i minus 8i squared. Now, I squared is negative 1. So we can replace that I squared with negative 1. And we get negative 6 minus 16i plus 8. Now, those are like terms, so 8 minus 6 is 2. And our solution is 2 minus 16i. Okay? So let's do another one. Negative 5 minus 3i times negative 1 minus 2i. Okay, remember, I squared is equal to negative 1. So we'll start at the beginning. What better place is there but to start at the beginning? So negative 5 times negative 1 is positive 5. Then we have negative 5 times negative 2i, which is positive 10i. Then we've got negative 3i times negative 1. Negative times a negative is a positive 3i. And then we've got negative 3i times negative 2i. Negative times a negative is a positive 6i squared. Okay, so we'll go back to the beginning. We'll combine like terms at the same time, deal with the I squared. Okay, so we've got 5 plus 13i minus 6. Remember, I squared is negative 1. So we have a positive 6 times negative 1 is a minus 6. So 5 minus 6 is negative 1 plus 13i. Very basic, very simple. Just remember, your I squared is equal to negative 1. Now, the last part of this lesson is dividing imaginary numbers. Okay? So, for some reason, somebody along the line somewhere said you're not allowed to leave an imaginary element or a radical in a denominator of a fraction. So if we had something like 3 over 2i, we would need to rationalize that denominator. We would rationalize it by multiplying by I over I. Okay, so multiplying straight across the top, 3 times I is 3i, and 2i times I is 2i squared. But remember, I squared is equal to -1. So -1 times 2 is -2, and we can pull the negative out front and get -3i over 2. Okay? The same thing goes for radicals in the denominator. We would need to rationalize away that square root or radical in the denominator by multiplying by that radical over itself. Okay, so 3 times the square root of 2 straight across the top is 3 times the square root of 2. The square root of 2 times the square root of 2 is the square root of 4, which, of course, the square root of 4 is simply 2. Okay, so that's the idea of simplifying when you divide imaginary numbers. Okay, so we are going to do just that. Say we've got 3 divided by 2 plus I. Okay, so we're going to multiply because we don't want that denominator to have an imaginary element in it. We are going to multiply by the conjugate of the denominator. So the conjugate of 2 plus I is 2 minus I. So all we've done is kept the numbers the same, the real part and the imaginary part, and just changed the sign in between. For example, if that was -2 plus I, the conjugate of that would be -2 minus I. If that was -2 minus 3I, the conjugate of that would be -2 plus 3i. Okay, so these are conjugate pairs. All we're doing is changing the sign in between the A and the B parts of our imaginary numbers. Okay, so we are going to multiply that fraction there by the conjugate of the denominator, because the denominator is what's got the imaginary part in it. If you have an imaginary part in the numerator, that's totally fine. What's not fine is keeping it in the denominator. So we have to distribute here in the numerator. So 3 times 2 is 6. 3 times -I is -3i. Okay? And then in the denominator. So I'm going to show you what happens here, and then I'll show you the shortcut. Okay? We're going to multiply 2 times 2 to get 4. Then we'll go 2 times -I to get a -2i. And then we'll go straight to these middle terms here to get plus 2i. And then finally, we'll go to the outside terms and get minus I squared, because negative times a positive is a negative. Okay, so what's always going to happen when you multiply a number by its conjugate is those middle terms will always subtract each other away. Always. So basically what that means is that the only parts of this that you need to worry about multiplying are these real parts here. So 2 times 2 is 4. And then the imaginary parts right there, minus I squared. All of that middle stuff doesn't matter because it will always cancel out by subtraction. So I squared is -1. So 4 minus a -1. And then, of course, minus a negative is 4 plus 1, which is 5. So let's do another one. We'll do another simple one, and then we'll do one that's a little bit more involved. Let's do 2i over -4 plus 3i. Remember, it's okay to have imaginary elements in your numerator. So it's what we're doing is we're multiplying by the conjugate of the denominator, because that's where our imaginary is, and we don't want it there. So the conjugate of -4 plus 3i is -4 minus 3i. And then we will do the distribution. 2i times -4 is -8i. And then we'll go 2i times -3i is plus 6i squared. And we will worry about fixing that in just a little bit. Okay, now we're going to distribute the real parts of the denominator. So -4 times -4 is 16. And then the imaginary parts. So minus 9i squared. Okay, now we're going to deal with the simplifying of the I squared. So we have -8i plus 6 times -1 all over 16 minus 9 times -1. So in the numerator, we've got -8i minus 6. And again, we'll deal with that standard form in just a minute. And then -9 times -1 is plus 9. Okay? So in standard form, the real part comes before the imaginary part. And 16 plus 9 is 25. So there's our final solution. Okay? Now, the more complex versions of these simplifying division problems, let's say we've got 3 minus 4i over 6 plus 2i, okay? And we are to simplify that, okay? We're going to multiply by the conjugate of the denominator, which is 6 minus 2i over itself, okay, because that's equal to 1. Anything over itself is equal to 1. So when you multiply a 1 into your original fraction, you haven't changed anything, okay? So now we will begin the FOILing process here. 3 times 6 is 18, and then we'll go from 3 to the -2i, so minus 6i. Then we'll go into the middles here. -4i times 6 is -24i. And then finally, -4i times -2i is positive 8i squared. Okay, and then we'll deal with that simplifying after we do the denominator here. So the real parts, 6 times 6 is 36, and the imaginary parts minus 4i squared. Okay, so let's go back to the numerator, and then we'll combine like terms. We would get 18 minus 30i plus 8 times -1 all over 36 minus 4 times -1. Okay, so we're getting there. So 18 minus 30i minus 8 all over 36 plus 4 will give us 18 minus 8 is 10 minus 30i all over 40. Now, what we're going to do when we finally get to that result is if everything can be divided by some number, then we will simplify by dividing by whatever that greatest common factor is. So everything, 10, 30, and 40, is divisible by 10. So 10 goes into itself once. 10 goes into 30i, 3i times, and 40 is divisible by 10 4 times. So that is the most simple version of our answer. So let's do one more like that. Okay. So let's do -1 minus 6i all over 2 plus 4i. So we multiply by the conjugate of the denominator, which is 2 minus 4i divided by itself. And we will begin now the FOILing process. -1 times 2, -2, -1 times -4i is plus 4i. -6i times 2 is -12i, and -6i times -4i is plus 24i squared all over. So you're as you see here, the denominator now has become the easy part. 2 times 2, 4, and then all we have left to worry about is the positive 4i times the negative 4i, which is -16i squared. So we'll combine like terms in our numerator. 4 minus 12 is -8i plus 24 times -1 all over 4 minus 16 times -1. Okay, so -2 minus 8i minus 24 over 4 plus 16. So -16 times -1 is a positive. So we get -26 minus 8i all over 20. And here, everything is divisible by 2. So -26 divided by 2 is -13. 8 divided by 2 is -4i, and 20 over 2 is 10. And there is your solution simplified. Okay. So there you go. Hopefully I did that section 5.5 justice without having my book. Okay, you have 2 IXL assignments that go along with this. So have fun with that. Tomorrow, we're completing the square.